Let us move on now with the third example, and this time you can try and do it yourself, as we already got some practice with the first two. So this is the transfer function. The goal is always the same: design a controller under specifications 0 steady state error, phase margin greater than 45 degrees. So greater means that it can be more, of course, and crossover angular frequency omega c 0.4 radian per second. Notice that differently from the last case, we do not have a pole in 0 over there, so no integrators in the loop, but we have a pole with negative real part, double pole actually, which tells us that the method which we use can be used. So you can try and do it yourself if you wish, otherwise just stay tuned for the solution. How? Well, you remember the starting point is draw the Bode diagram of H. How do you do it? Well, you can either do it by MATLAB or either draw it with the rules that you have seen previously. It is not very difficult to do actually. Once the Bode diagram is drawn, then you need to think about how to change the crossover angular frequency at the value that you wish, and how to get the desired phase margin. And of course this will tell you also which kind of controller you need to choose. A first part of the solution is to formalize these requirements, so you can try and do it yourself, otherwise it's coming up right now. So this is the Bode diagram, as you can see over here. If you pick C, the controller, equal to 1, then the loop transfer function is just equal to H. So in order to fulfill the steady state requirement, you need one additional integrator in the loop. So this will oblige us to choose a controller with an I part, so either PI, PID, etc. The desired crossover frequency is 0.4, which is here. Now it is crossing at 0.2, which is not okay. And at 0.4 over here, if we move the crossover over there, we'll need to have at least 45 degrees of phase margin, so it means at least 45 minus 180 degrees. And actually we are already fine with this if we are happy to have a little bit more. We have minus 126 degrees right now, so we have about 50 degrees of phase margin, which is okay, considering that we have a requirement of having more than 45. So we have two constraints, two equations, one coming from omega c and the other one coming from the phase margin, which actually is not really an equation, it's more an inequality. And then we need to put an integrator in the loop. So this will lead us to the choice of controller, and then the equations will come for tuning the parameters. I guess you can all make this choice of controller by yourself, otherwise we'll see it in the next page. Of course, the choice is a PI controller, 2 degrees of freedom, P part and I part, and we get the integrator that we need. So PI controller, you can take it from the catalog of the beginning of this class, last class, sorry. And then here it is. Now we just need to tune Kp and tau I, Kp greater than 0. So there are two methods you can think of. The first method I call it precise tuning, so we'll just target exactly 45 degrees of phase margin for the system. So then we need to set the phase, the total phase of H plus the phase of C at 45 degrees. So what is the phase of H? The phase of H at this point, it has been computed over here. It is minus 126.8. So if you want to move it to minus 135, which yields the 45 degrees of phase margin, then we need to increase it of this difference. Basically, we need to increase it of 8.2 degrees, right? We need to increase it of 8.2 degrees. So then that's it. This is the phase we get here. The phase we get here. We set it equal to minus 8.2 degrees. Notice we need to bring it down. We are actually decreasing the phase margin. We said previously that if you don't do this, you have more than 45 degrees. So we decrease the phase margin. So we set the phase of C equal to the additional term that we need to bring it down a little bit. And the phase of C is the phase of the numerator minus the phase of the S, let's say, of the denominator. So phase numerator is arctan of imaginary part omega C to I omega divided by the real part 1 minus phase of J omega C, purely imaginary number, so minus 90 degrees. And this has to be equal to this number over here, just by solving for tau I omega C, which means getting tangent on both sides. After moving this to the other side, we get that the tau I is the tangent of 81.8 degrees divided by omega C. Omega C is 0.5 radians per second, which yields the 17.3 seconds. Remember, tau is a time. You might ask at this point why we want to decrease the phase margin. Well, it can make sense not to have a too high phase margin, because maybe maybe I haven't said this before, but phase margin is good in the sense that it gives you stability, but it always also slows down the system. So if you want to have a system that reacts quickly enough, you should not pump up the phase margin too much. So it makes sense to keep it around 45 degrees in this case, but in general something between 60 and 30 degrees should suffice. You don't need to push it higher than this. Anyway, this is the case in which we have made the choice of tuning it exactly at 45 degrees. So I hope everybody remembers how to compute the phase of H at omega C. The phase of H at omega C will be the phase of the numerator, which is 0, minus 2 times the phase of phi j omega C plus 1, which is 2 times the arctangent of omega C times 5, right? So once we have found tau, then we can move on and find Kp. And in case you haven't done it yet, you can maybe think about it, how to do it. We have set the phase at the crossover frequency, but we haven't really set the crossover frequency yet. So we need to tune P in order to Kp in order to get 0 dB for omega equals 0.4 radians per second. How we do it? Well, the modulus of L, which is the modulus of H, plus the modulus of C in decibel, or otherwise the modulus of H times the modulus of C in units, has to be 1, which means modulus of this computed at omega C will give us to the power minus 1 the modulus of C at omega C again, which you see written here. Okay, the product of the two has to make 1, which means 0 dB. So that's how it has to be. So the modulus of C is just Kp times modulus of the numerator divided by modulus of the denominator. Here you know the rules. Imaginary part square plus real part square and the square root. Here you only got an imaginary part, so the modulus is just the modulus. And then this must be equal to 1 divided by the modulus of this, which is 2 goes at the denominator, and here you have square root of imaginary part square, real part square, but again square, so the square root goes away. By solving for this, you get the value of Kp. Easy. The second way you can tune this, and you get the second controller, which we call C2. We notice that the phase margin can be greater than 45. So we do not need to bring it down, as we said before. We don't need to bring it down. So instead of setting tau I in order to get exactly 45 degrees of phase margin, we'll do another consideration. Just look at the Bode diagram again. If you remember the PI control, well, it is given by this formula over here, right? Which means it starts with a minus 20 decibel per decade slope, because we have a pole in 0, and then at a certain point you get a 0, which brings the slope up again to 0 flat. And this means the phase starts at minus 90, and then it will go eventually at 0. So if we do not want to have a phase going too much down from this situation, we said this situation we already have a phase that we like. But if we add an integrator, this one could go down. What we need to do, we need to make sure that the pole of in 0 is counteracted soon enough by the 0 at the numerator, sorry, this one, so that the phase goes back at 0 degrees early enough before the 0.4 radians per second. Okay, so let's see how we do this. Well, it's enough just to set Ti slow so that the 0 will come at low frequency. Let's say Ti should be bigger than the 1 over omega c, let's say. In this case, we just take tau I equal to 10 times divided by omega c. Then we can verify, computing the phase of the loop transfer function overall, that it is still greater than the value we have set. So in fact, you can check that the phase margin is still greater than 45, which is okay. And then you can finish off this example computing the gain of Kp, in this case, again by setting the value of the modulus at 0.4 radians per second equal to 0 dB or equal to 1 in terms of units, and this will give you Kp. The two tuning don't give a very different result, because the difference in terms of phase margin is really small. And this is the first tuning, we call C1. This is the second tuning, we call C2. And you can see them drawn in the Bode diagram here. And you can see that for both, you strike 0 dB at 0.4 radians per second. There is a little bit of difference in phase, having the second one a little bit more phase margin. Same story in the Nichols chart, or Nichols-Black diagram, if you like. Step response also doesn't change a lot, but we got what we wanted. So this is the response to a unit step. Eventually goes to 1 exactly, so 0 steady state error, which is what we were asked in the beginning. Last example. So is again same transfer function, we just got a slightly different specifications. Phase margin at 50 degrees, again 0 steady state error. The crossover is different, and it is a bit higher. So we have what we can say a higher pass band for the closed loop. Again, you can try and do it yourself, otherwise stay tuned for a solution in 3, 2, 1. So same as before. Now let's just check what we got at 0.8 radian per second. The phase over there is too small, because we want to have 50 degrees of phase margin, so we need 130 minus 130 degrees. Instead here we have minus 151. So we'll need to lift up the phase a little bit in this case. So just to compare to the previous case, the second tuning method would not work out. We really need to pump the phase up. So we have two constraints and one integrator needed, and so I just let you think about what we can do to which kind of controller we can choose to solve this problem. Be careful here. Now we need to bring the phase a little bit up. We need to bring it from this value to this value. So maybe we need a different choice with respect to the previous case. Yeah, in fact, we cannot take a PI controller because the PI controller has a phase going either 0 or minus 90 degrees down. Here we need something that brings the phase up, so we'll need to introduce a D part. The D part, you remember, can bring the phase up to 90 degrees up. So we pick a PID control. We cannot give up the I part because we need an integrator in the loop due to the steady state error specification. So the PID, you can write it like this. Work out the products, you get this stuff over here. If we make the approximation that we said earlier on, that usually tau I is slower than tau D, so it's bigger than tau D, so you can just sum tau I and tau D together and make them equal to tau I. So basically you can use this approximate formula over here, which is nice because basically you can separate the numerator into two contributions. One is let's say a low frequency 0, and either is a higher frequency 0 if you wish. So the point is, if you think about this this stuff, how it works in terms of Bode diagram, starts at minus 90 degrees of phase due to this guy at the denominator, and then the two poles, the two zeros here, sorry, will bring the phase at plus 90. So we have to make sure that these two guys, these two zeros, are before 0.8 radians per second, the desired crossover frequency, in order to have at the crossover frequency a positive phase gain. You remember we need to have an extra 20 degrees. This formula over here, it's easier to get it from the end to the beginning. If you work out the product, then you get this one over here, then you approximate the sum of these as tau D, and you get this stuff over here. One of the tutorial works this out as well, I think the last tutorial, so you can have a look at that as well. At this point, I say there are countless possibilities to complete the tuning, because actually we have only three equations, and we have only two equations, two constraints, omega c and the phase margin, but we have three parameters, so basically you can fix two parameters according to your taste, and then the last one will be arbitrary. So two equations will fix the parameters, but one is free. So you can do it in countless ways. The first method I propose, you tune the integrator first, and then you tune the derivative, and we get a controller I call C1. So we just copy from the last example. We set arbitrarily tau I equals 16 seconds, the same as in the last example. Remember what I said, we have three parameters, so two equations, one parameter is free. That's what I did. I just got tau I free, let's say, arbitrarily. Not too arbitrarily, it has to be a wise choice. As I said previously, we have to make sure that tau I is low enough and comes before 0.8. This zero comes before the crossover frequency. So 1 over tau I must be smaller than omega c. That's exactly the same criterion we did before. So this is the case, that 1 over 16 is way smaller than 0.8 radians per second. So once we set tau I arbitrarily in this reasonable way, then we can just get the phase and get tau D. So the phase at omega c is the phase of H plus the phase of the controller. This is the phase of the PID controller, right? And at this point, at omega c, we need 21 extra degrees. 21 is the difference between minus 130 and minus 151.9. So the contribution, the extra contribution of the controller must be this value. And then here tau I is known, omega c is known, only tau d is unknown. And if tau d is unknown, well, you can just factorize, say, collect all the terms on the right hand side there, then take the tangent, and you get tau d. And you see, as we said, tau d is more than tau I, which is the hypothesis we did in order to get the simplified equation. I'm using the simplified equation here for computing the phase, so that's fine. Yeah, then the second part of the tuning is just making sure that omega c is the crossover frequency, and then again means modulus of L at the crossover frequency is 0, which brings to this. At this point, I guess you know how to do it. So the modulus of the PI controller at omega c must be 1 divided the modulus of this guy at omega c. Factorizing everything all together, you can try and do it and see if I got it right as well. You should get this expression over here, which gives you this value. Let's see, this is a possibility, not the only possibility. There is a second method, so we do the other way around. We tune the derivator first, and then we tune the integrator. So again, how do we tune tau d? We take it arbitrarily, but as we said, we need the contribution of phase at least developed enough at the crossover frequency. So if you look at the Bode diagram of the PID controller, or in general a Bode diagram of any system with a 0, you get a 45 degrees extra exactly at the 0. So you know, when you have a 0, the phase will grow of plus 90 degrees. But if you take it exactly at the 0, you already have 45 of them. So then we choose to just put tau d exactly at omega c. So at 1 omega c, let's say. And this, well, not really exactly. We just, instead of doing 1 over 0.8, we just take it at 1. We said it's a reasonable choice. It is arbitrary. So we can pick whatever we want reasonably. And then we do the same equation as before. We make sure that the extra phase given by the controller is this 21.9 at omega c. The equation is the same. The only difference is that now the unknown is not tau d, but is tau I. You can work it out and you get this value for tau I, which is greater than tau d, and which means that the assumption we did is okay. And then you can finish it off again by setting Kp in order to have 0 dB for L, which is H times C, the sum of C, the sum of H in dB, equal 1, 0 decibel at omega c, which gives you this Kp. So C1 is the controller we tuned by setting the integrator first and the derivator later on. C2 we did the other way around. You can draw the Bode diagrams. They look a little bit different this time. It's not like the last case, but they do the same job, and you can see they do the same job. They hit 0.8 radian per second, both of them. And also the phase margin is more or less the same. We do not have exactly 50 degrees in both cases because we use the approximate expression of the phase. So we get a little bit of uncertainty. That's why it's good to draw them at the end. Are they good, both of them? Yes, of course. One a little bit more than the other. We said at the beginning that the phase margin has to be approximately 50 degrees. So no problem for that. This is also something that probably worries the students a lot. In many cases, the tuning can be done in an approximate way. So if we ask for phase margin of approximately some values, it means that you can just solve it by looking at the graph, for example, or using some approximate expression, etc., etc. If we wish instead to have exact values, then you have to do the computation like we did in the previous examples. Same story in the Nichols chart, where you can see the same behavior, right? And then let's finish off with the step response. Well, a bit different, but both of them steady state 1 equal to the amplitude of the step, which means 0 steady state error. And that basically was it for this class and for the course. So basically, the real deal of all we have done is to be able to do to solve exercises, to solve problems like the ones shown in this last 6th class. And these you will see some examples in the exams. Typically, we have 2 examples of exams in Moodle. You can have a look at them. Also, the tutorials are preparing you for that. Especially the last tutorial number 5, has some kind of tuning problems which are very similar to this one. So, in order to be able to do this, you need to be a bit expert on the previous parts, but the most important thing is that you are able to tune a controller. So tuning a controller means being able to understand the Bode diagram, knowing both the criterion for stability, and being able to find alternatives if you cannot apply it. And then if you are required to tune a controller with the frequency domain specification, being able to propose a class controller, or maybe even not, and then tune the parameters according to specification. And we have seen actually the specifications are not so many. We just seen a few. We have the crossover frequency, which is basically equivalent to the pass band of the closed loop. We have seen the phase margin or gain margin, assuring stability and the damping of the closed loop function, and then the requirement on the steady state. So basically we haven't seen a lot of things, and all the possibilities are kind of limited in the scope of this class, and that's why I think it's not really difficult to achieve a tuning of a controller in these very simple cases. The tutorial will show you some example with some more maybe specific problems in terms of domains of application, just to make this all not so abstract as it seems at this point. So thank you for listening. I'm of course available to provide extra information if needed, as explained in Moodle, and also probably I'll add other videos if necessary on a specific topic if you just ask, probably. Thanks a lot, and see you next time, maybe in person someday, maybe not. Anyway, please everybody stay safe and good luck with this class.